All right, hi. I'm Richard Wareing. I'm a production engineer at Facebook. I'm actually on the Warehouse Foundation team. I used to be on the POSIX team working exclusively on Gluster, but now I've kind of branched out a little bit. I got to work on two other storage systems, XFS, and another one that we're replacing XFS with, which is warm storage. But Gluster is kind of the file system I still kind of always go back to. It's been like a huge source of inspiration, and when I come across things that I think is going to be like pretty impactful for the community, I always want to like try and bring that back and share kind of things I've learned. So in this talk, I'm going to talk about kind of a very underappreciated feature of XFS, probably something the XFS developers wish would probably just go away and never come back. I'm actually trying to dissuade them of that with some patches and actually fixing some broken tests in the XFS community. So it's real-time subvolume. Some of you may have heard of it. They're actually kind of like, if you've ever played with it, you've probably been stumped along the way and like, what the hell is this? How do I use them? I'm going to try and demystify that a little bit in this talk and actually show how this can be used in Gluster. We've actually are starting to use this in another storage system at Facebook with pretty good success. So quick tangent. Again, I kind of spoke. I had some perspective, I guess, over the last year and a half. Some things I've learned just looking at these other storage systems is like the Gluster translate architecture. This is actually really unique to Gluster. I think the fact that the specific translate architecture itself, although super elegant, I think the fact it provides a framework for Gluster is just extremely powerful. And in these other storage systems I've worked on, they kind of lack this, and this creates like developers getting really creative all the time. And if you look at different pieces of the code base, it's like you can really tell it was 10 different people that wrote this stuff, and it makes it really difficult. Gluster doesn't have that problem. Don't ever give this up. And it provides this like good isolation between components. Yes, there's cheating in various translators, but it's probably more isolation than you'll see in most systems. I/O latencies, all of the systems I've worked on, Gluster is king on this. It is super, like we're talking like orders of magnitude difference. Just people are not able to achieve these latencies. That is something that I think Gluster really excels at and is unique at. Simplicity, I think I've spoken about this before, and the open source community. Like this is one of these things I just like hammer into our engineers. They're like all about the proprietary software. This is just such a huge asset for companies that use it, and then the software itself. I think things I've also learned is like some things I think Gluster needs to kind of work on to really go to that next level. Like a lot of people come to me when I've been like working on these other systems, are like, oh, can't we just like swap this out and put Gluster? And as much as I'd like to say yes, there's things that prevent that, and like one of them is like scaling. Like there are like a great many use cases out there that would like move away from XFS tomorrow in favor of something like Gluster if they could simply just have much bigger namespaces. So instead of like a few petabytes, if it could be like tens of petabytes or hundreds of petabytes. So this is like one thing. I think Facebook, we're definitely going to try and contribute in this area because I think we've got the resources to go do it. Code quality. XFS is awesome for commenting. If you go look at their code, it is a dream for people that have never seen their code before. Gluster, I think, has gotten better of this over the years, but probably still needs to push on this. JBot support, Gluster typically requires hardware RAID. I know we've been playing around with software RAID, I guess we're pretty close. But JBot is kind of what a lot of systems, or a lot of like, we'll say the larger scale systems support, and it's like due to cost. Drains rebuilds, I think there's going to be a talk on this a little bit later. I think Shreyas might be getting into this. There's some XFS tricks around this, but Gluster itself is actually kind of pretty slow on this. You know, it takes often weeks instead of days, so like that's kind of like what we're competing against. So I think those are things like just to keep in mind of like places that we can have impact to actually improve things. Okay, so with that kind of rant out of the way, GlusterFS and metadata. I'm gonna like preface this by saying Leveraging the underlying file system for metadata storage, like I do not contest this. This was actually, I think, like a really smart choice by the Gluster developers. Other systems have like these central metadata stores. XFS has name nodes. Another system we built called Warm Storage has something similar. The big benefit, I think, on this, just looking at all the other ones, is like simplicity. Like, and ultimately, what comes out of simplicity is like reliability. Like you get into this pattern of just whack-a-mole problems as soon as you like take that metastore and put it somewhere else, because you've got to like somehow map that metadata back to the data blocks, and there's just a lot of code and complexity to make that happen and actually keep consistency. But this isn't like without problems. Gluster has like a super heavy reliance on the file system being good at metadata. It's also got issues when it comes to things like mkdir patterns. And what? Okay, so this is like the classic mkdir problem. We make a directory, we magnify it. One single OS will magnify into potentially hundreds or even thousands of different VFS operations. So depending on what one of our customers is doing, this can get like really ugly really fast. And of course, throughout the years at Gluster, we've had some tricks to reduce this. So we'll do things like redir optimize. So if you're reading a directory, we'll maybe cheat and go to like one subvolume and get the data. You can even envision, you can do things like, we'll go find the fastest children on the subvolumes, and like we'll go get the data from that, so long as they're consistent. But this is ultimately, like, there's limitations on what we can do with this. And what ends up happening is something that maybe should take, or maybe what a user might be used to a couple milliseconds, we kind of gross that up to like tens of milliseconds or even far longer. So, like, okay, great. Like, but is this like really a problem? Can you prove it? If you spend some like quality time with a tool like BlockTrace and actually go see what the I/O patterns look like down to the disk, and actually encourage like people like go do this and go look at like the RWBS field in BlockTrace. This will actually tag the I/Os as they go down to the drive and tell you which ones are metadata related. You do this, you kind of crunch the data, and for a create heavy workload, you may come out with a pie chart similar to this. This is from one of our actual clusters. And you'll see here that like 51% of all the physical IOPS are metadata. So that's a problem, but it's also maybe an opportunity, because if we can figure out some way of solving that problem, that's like a ton of IOPS we can like reclaim and like dedicate to kind of more the thing we really want to be spending those IOPS doing, which is like reading data or writing data. So example 2, this is like an mkdir heavy workload. This is like even worse. And that create one back there, that's actually like kind of a, people using Gluster as almost like a blob store. It's not the best use case, but it happens. The people, effectively Gluster often is a better blob store than purpose-made blob stores out there. So this is like an mkdir heavy workload. This is like, I kind of call this as like people using the file system as a database. Again, please don't do this, but people do it. It's often used for prototyping a new idea. And if you actually, again, do BlockTrace, you'll produce a pie chart like this. 83% of all those physical IOs are metadata. Again, that's like super expensive, not how we want to be spending those IOs. So traditional solutions to this problem, people typically will use page cache. So hopefully maybe Linux actually like caches some of these metadata operations. This is like, not a bad solution. It's super simple, just works on any storage system. The cons, this heavy reliance on how much DRAM you have on the system, limited space to cache objects, and doesn't really help with write-heavy use cases. And dedicated metastores. So this is the like HDFS and another storage system we're building called Warm Storage. This is and even I think like Steph takes this approach as well. Good designs can scale really well, but they're not without their complexity. And I think anyone who's actually worked on one of these, it's actually a pretty challenging to get these things right. And they present kind of their own scaling limitations, because as soon as you make a metadata store, typically they're making them to maybe like tens of machines, and they're making trade-offs because like if they want to go to, if you ask them to say, well, I want to have my metadata store 100 machines wide, suddenly their design choices completely change. So they even have like limitations when they were designing these things. And kind of with the Gluster ethos is like, we really want to try and be like scale out on everything, and not really have any kind of points where we're making these trade-offs. So, one question is like, can we combine the best of both? And this is where XFS with real-time subvolumes can maybe come into play here. It's horribly named. The XFS developers will be the first to tell you this. The name comes from, it's real-time in the sense that it's providing predictable latencies, which is a common requirement for quote-unquote real-time software applications. They kind of want to be able to do I/O to systems and kind of like set their watch to it. They don't want to have like 10 milliseconds, and then something jumps to like 50 milliseconds. They want like 10, 10, 10, 10. The other key thing about this is they're not trying to win an absolute latency race here. They're trying to be consistent. So if you were to like just like go compare this against like a normal the AG allocator for XFS, AG will win in some cases, but where it's not going to win is on consistency. So you have to like keep that in mind. Current use cases for this are media streaming, typically like PVRs. There's not a lot of people actually saying like, if you like do some research on this, there's very few people that kind of admit to using this, but there are use cases out there according to the XFS maintainers. This is also additive. This is like one of the key things to keep in mind with real-time subvolumes. This is not replacing the traditional data subvolume that you actually like use if you use XFS. This is like an extra subvolume alongside of it. We'll get into like how this actually works in a second. Other thing to keep in mind, XFS has two allocators. It's the real-time subvolume allocator. This is a completely different data allocator than the AG allocator that you're typically using on XFS. And the implications of this allocator is that it's single-threaded. So the AG allocator has like multiple locking domains, so it's actually quite good at multi-threaded workloads. The single-thread allocator is a single locking domain, so you have to like use this wisely. The good news is like you still have these two locking domains, or two different allocators, so if you use them wisely and you can envision like, hey, maybe small file I/O, maybe that makes, that's probably more likely to be multi-threaded, and like the larger writes that you might be serving might be more suited to the real-time allocator, and indeed that's typically the case, at least what we found. So this is an overview how you can like visualize the real-time allocator in XFS. You'll have like your normal XFS file system here that you're used to, and in an XFS world, it translates to this. You've got on your standard block device, or what they'll refer to in XFS as just like the data block device. If you use XFS info, they actually kind of like, almost like, I would call it like erroneously calling it like the metadata device, but it's really like the data subvolume. And on that subvolume, you're going to have like your metadata, your log, which can be optionally moved. Most people know that. And then you've got your data blocks. And then you get this extra thing down here called the real-time block device, which contains the real-time data blocks. Digging a bit into the real-time allocator, it's actually really simple. One of my critiques on a lot of software engineers I met working on storage is they have this like really fascination with creating a raw, like writing raw block. Like this is like, you meet like a lot of these people, they all want to like make a raw, like they go like XFS, ext4, this is all garbage, I can do it better. And then, it's kind of like, go ahead, like, yeah, I'm sure these like people that have been working on XFS and ext3, they're all crazy. They, what have they been doing for like, 20, 30 years? And usually what they end up doing is coming up with like a worse implementation of this. Which is basically taking a drive, slicing it up into chunks. They'll maybe go through an interlude of some form of garbage collection, which they may later find out is actually maybe not the best decision. I think there's cases of like things like LevelDB has done these things, and there's kind of like MySQL versus LevelDB debates on this. But I think a lot of the time they end up with something like this. So my kind of like, my hint here is like, just use this if you're tempted to do raw, because try this first. You basically can chop the drive up into these fixed extents, and you can make like the obvious trade-off is, yes, if you write small files, they're going to be burning some amount of data. But the idea here is you're like making this conscious choice to optimize your fragmentation. Like you're trying to keep the fragmentation at a minimum here, and this again provides you this predictable latency that these real-time subvolumes are trying to do. Because of course, if you chop your drive into Swiss cheese, you're going to get like varying latencies based on the different fragmentation levels you hit in the drive. Okay, so one of the other challenges when you're using real-time subvolumes on XFS is like the documentation is absolutely horrible. They're including this lovely undocumented option that actually kind of like unlocks a lot of the coolness of this feature. So when you're doing an MKFS, if you want to like try this out, the thing to also keep in mind is your real-time device is where the data blocks are going if you set this RT inherit to 1. And what this RT inherit to 1 simply does is it's basically setting a flag on all the directories, which is saying when you write data to that directory, store the data on the real-time device. That's it. As soon as you do that RT inherit 1, you've now like forked your metadata to one device, and you've taken your data and put it on another device. With Gluster, the obvious thing here is like, hey, maybe if I choose an SSD for my data device, my metadata can be on this really cool, fast device while my data is on the cheap hard drive. This is the exact kind of like use case that we're using and we're looking at. We haven't started using this on Gluster yet, but we are going to be using it. We already are using it on another storage system, and the results are actually pretty awesome. Like what we found is we get like less than half the latency. We saved like over half the I/O. And it's just like, and you can even, as I'll get into, you can even get into, take it one step further and actually start caching even like small files on the SSD. So, okay, so also things to get to know is like if you've never used XFS IO, this is actually a good command to get to know. It basically allows you to execute internal XFS operations that aren't necessarily accessible by normal POSIX tools. So the one here is if you want to actually like list the flags that are on a directory, you can do so, and you can actually see like the real-time inheritance flag. You can also do something. Well, I'll get to the next slide, and I'll show you that. So if you do that, like you can use this out of the box. Gluster now has its metadata on SSD. You've done nothing. You didn't even write a line of code on Gluster. You've now got like lightning fast metadata, and your LSs should be a dream, and your data blocks are on your hard drives. Where I can see this going and where I think the community should consider taking is you can envision like a real-time translator, and which could provide you like a much more simple form of tiering. And in this case, you could basically create you can create a directory in your directory hierarchy called like .cache. And anything you store in that .cache directory, just by stripping off that flag, will now go to the SSD. Done. Simple. Like you'd be able to like write this tiering translator probably in like a few weeks, and keep all the tiering logic local to your brick, which is like easier to test, easier to implement, like much simpler. So with that in mind, how might you actually set up your bricks on a machine? Probably something like this. And indeed, this is actually how we use it in our warm storage system. And yeah, basically, so for Gluster, it maps basically the exact same way. We have our drives, SDB, the SSDs would be SDB, the hard drives are SDC and SDD, and the SSD, you can basically have like one SSD, which is storing all the metadata from multiple drives, or multiple RAID arrays. It all depends on how you want to do this. If you're a little bit more nervous, I will say like AFRs on SSDs are low enough, you typically can get away with this and be okay. Just don't buy like a thumbnail drive, obviously, like buy like a decent SSD. And you can basically just partition that into like 2 or 3 chunks. The metadata on XFS is actually really, really tiny. For 1 million files, it's something like 3 gigs. So that can give you an idea of like just how much metadata you can store in an SSD. And then you can basically like take those partitions and you map them to your RAID arrays, and away you go. And this is, and again, this is not in place of RAID array. This does not solve necessarily like, this is not trying to solve say the JBOD problem. That's like a totally separate thing. So after combining this, I think you get like the best of both worlds. So you get like simplicity. It just works. There's no changes to GlusterFS core. Works on any storage system. I've got this running on one Gluster test cluster already at Facebook. Now that I'm kind of done with this other use case, I'm going to be like focusing on that. And works with a write or wow, okay, that's bad. Ready, heavy metadata to work on. No, I don't know what I was trying to say there. Okay, and SSD-based file caching, which is just trivial to implement. Now, there are some cons on this. It does not scale independently of bricks. This is the classic reason I think people give to make like separate like caching tiers. But I guess I've just yet to see one of these things that has like been implemented in like a really reliable kind of bug-free manner. And this is like multiple storage systems. This is not like a knock on Gluster or anything like that. It's a really hard problem to solve, and I don't think anyone has actually like nailed this yet. So I think there it's like just it's this. Yes, it's just like trade-off you have to make, because like it will not scale independently of the actual Gluster cluster. But I guess like one question is like, you know, what do you care about more, reliability and simplicity, or the ability to do that? And I guess that's like dependent on the use case. The other cons, this does require some, I'd say, like modest changes to the kernel. As you'll see in the next slide, we've basically made 3 tweaks to kind of get this all to work. 2 of which I'm still waiting on some XFS maintainers to approve. And it's single thread optimized. This is one of these things that I think is going to need a little bit more exploration to see how this actually interacts with Gluster. To date, I was really worried about this actually in like this other use case that we've been working on, but it really hasn't surfaced as a problem because like basically you make this trade-off by like you liberate the system of all the, or like give it back all these IOPS from metadata, and that like more than balances out this hit you take on the single-threaded. As for the tweaks we've made, StatFS, so if you've tried to use this in the past, one of the kind of like really confusing things you might have found is like you like set this thing up, and then you can see how much space you have in your SSD, and you have no idea how much space is on the actual like hard drive. And usually at that point, people give up. And the answer is you've actually not done anything wrong. It's just that the system was not returning StatFS to, I think, the thing that most people actually intuitively thought it would, which is the hard drive, especially if you're using like RT inherit. Because what you're saying there is, I want my data stored on the data device. And if you're doing that, you probably want the StatFS information to return from the data device. So this patch basically detects this flag and then returns like what I would call the more intuitive answer, which is like your data device status. The other 2, and so that patch has been reviewed, and that has been approved by 2 of the maintainers. These 2 are still pending. We're kind of going back and forth on these. There's a little bit, I think they're more controversial on the XFS mailing list. RT Alex size, its goal here is to provide kind of like a simple form of, I won't say tiering because Dave Chinner will kill me, but it basically will store the data on the device based on the first allocation. So if you allocate a small amount of data, it may allocate it, or it'll allocate it to the data device, in this case an SSD. And if you take a big allocation, it'll put it to the hard drive. This gives you kind of like, you know, a kind of very cheap, naive form of tiering, but the obvious thing it will not handle is appends. So in that case, the system like Gluster would be responsible for like kind of intercepting an append, and as a file grows to actually like migrate it off. Maybe this can be handled inside XFS one day. I don't know. It'll depend on a lot of things, implementation and support from the XFS maintainers. RT fallback %. This is to guard against kind of the obvious thing that's going to happen here is like you fill up your SSD, and then even though you have all the space left in your hard drives, you may be screwed. So this basically can protect a certain percentage of your SSD space and then fail back to the RAID device in the case that it's getting full. And typically in the cases where we've been using this, it's like, we'll set it to like 50%. So we want like a ton of the SSD left over to be conservative. And this just kind of like the basic logic of these patches. For RT Alex size, we're basically saying we get a VFS write, we go look, is it larger? If it is, we send it to the real-time subvol. If not, we'll send it to the SSD. And again, append's not handled currently. And the graph, and then the chart changes a little bit with RT fallback. We have like an extra check in there. That's it. Questions, comments, concerns?
Hold on, I'm coming. Hold on, I'm coming. Relax.
So what's the nature of performance improvement that you have seen with this?
So when I tried it on Gluster, I went from, the thing I did was I basically healed back a brick. Like I turned it into one of these things and I healed it back. And so lookup latencies were like 0.1 milliseconds instead of like multi-millisecond. So that's what so Gluster seems to benefit quite a bit. We didn't get quite that on the other storage systems that we tried this on, but Gluster is also a lot faster. Like we would love millisecond latency, but we don't even get that. So.
So did you get to do the block tracing after doing this and kind of seeing what the percentage of data metadata is? Yeah,
so if you do block tracing on the thing to do after you've got a setup like this going is do your block trace on the RAID array, and what you should see is just pure reads, writes. That's it. Like you won't even see one single metadata operation. It's just like awesome. We actually see on and like the way we measure this on our storage systems, we have a tool called FBO trace that we haven't like, I don't think we've open sourced this yet. We probably will. But what it does is basically hooks into kernel trace points, and we take a look at sector aligned reads and writes, and we kind of merge those internally in the tool, and then we come up with like a coalesced I/O. And what we're measuring is we want to see like what is the average coalesced I/O size. The reason we coalesce it inside the tool is because sometimes the kernel just like chops up I/O sizes for various reasons, and we don't want to like we want to book these or do the accounting correctly on these because obviously in the drive there's no seek if they're sector aligned. So and what we found is we're able to like triple our average I/O size using a real-time subvolume versus not. So it's you not only get performance benefits, but you get like all these extra IOPS back to your storage system that you can use for reads and writes.
Other questions? Or do you want to continue? No. Cool. All right. Thank you so much.